Okay. I'm not. Okay. Yep. Right. So in the previous chapter, on chapter 2, you looked at hypothesis testing. So in the last chapter, in chapter 3, we were discussing on hypothesis testing for several parameters. Hypothesis testing test on population parameters. Okay, and we looked at for one population and two populations, right? So hypothesis tests can be of many kinds. Okay, the one that we looked at chapter 3 is on the population parameters. So we looked at one single population and two population in the case where you have one population and two populations. Okay, so today we're going to look at a new one, which is going to be when you have more than two populations. So specifically on the mean, only for the mean. So still on the population of parameters, but we're going to look at how to test when you have more than two populations. All right. Okay, so let's start. So this chapter is chapter 6 from your textbook. It's under analysis of variance, okay, otherwise known as Anova. Another word for it is Anova. So why this useful? Anova useful, especially when you have, if you have more than two populations, so you can test whether maybe you want to improve some performance of a process. I mean, like for example, that you observe the accuracy of a certain product. You observe the measurements of certain products, of different machines, of many machines, of more than two machines. So Anova would be useful for that. Okay. So one example, a simple example. Imagine that you have a speed of a car. Speed of a car. You want to observe speed of a car. So what you do is you take a car and you test it using different tire size. Okay. This different tire size is a treatment that you apply to the car so that you can see how the speed is. Okay. So this size of tire is also known as treatments because you are treating that to the car to observe the speed of the car. And to test the tires, you take, for example, two types of tires, a 16-inch tire and a 24-inch tire. So these would be called the levels of the treatments, okay, or levels of the factor. So the treatment are also called factors, where you apply the treatment to a car because you need to have a medium in order to observe the effect of the size of tires. And here you're using only two types. So that, therefore, this is the level of the treatments. Okay. So if I were to, let's imagine the observation is something like this. So these are the speed of the car. So these are the speed that you observed speed. Okay. So obviously these are from a sample, right? So these are samples. And this is the treatment or the factor. So do you have two of these? This kind of experiment is called a completely randomized single factor. Why single factor? Because you're only treating, you only observe this treatment based on a single factor. What are the single factor here? What is the single factor that you're observing here? Class? What is the single factor that you're observing here? Dengar ke? Tire size. That's right. So tire size is that single factor. If so single factor, you could have more than a single factor. For example, maybe you look at the tire size, maybe you look at the aerodynamic of the car. So those are two factors. But at the moment, we're just looking at a single factor, only one factor for these observations, okay? With two levels of factor. So here, each treatment has 1, 2, 3, 4, 4 observations. So you've got 4 observations. Sometimes they are called replicates. Okay. Right. What about this one? So this is another example. Our observations are tensile strength. So observations here are on the tensile strength. Okay. What is the treatment that's being applied? What is the factor in this experiment? For this example, what's the factor, or what's the factor of this experiment? Class? Hardwood concentration. So it is hardwood. How many levels are there in this hardwood concentration? How many? Yes, it is hardwood concentration. 4. 1, 2, 3, 4. What are the 4? You've got 5%, you've got 10%, 15%, and 20%. Okay? So we observe the strength of, for example, a pillar or something with different concentration of hardwood. Okay? How many observations can we see for each of the hardwood concentration? How many observations can you see for each hardwood concentration? 6, yes? 1, 2, 3, 4, 5, 6. What is the overall observations for this experiment? What is the number of overall observations in this experiment? 383. 383 is the 383 number of observation. Betul lah. Yes, that's right. It's 383. 383 ke? Bukan. 383 is the tensile strength. The number of observation is 6 times 4. That's 24. So this is 383 is the tensile strength. This is the sum of the tensile strength. So, okay, this 383 is the sum of the tensile strength. But the number of observation is 24. So you've got 6 observation of 4 levels, so it is 24. So the number of observations in this experiment is 20. Overall number, total number of observations. Total number of observations is 24. Okay. 383 is the tensile strength, the total of all tensile strength, observed tensile strength. The sum of all observed tensile strength is 383. Okay. All right. Mana ni? Ni. Okay. Now let's plot these observations here. Let's plot these observations. What's the name of this plot? Do you know the name of this kind of plot? Yeah, it's got a box plot or whisker plot. Okay, so this is a box plot. Can you describe to me about the tensile strength that you can see here? Can you see? Can you comment on the tensile strength that you observe in this plot? Can you comment? Positively, okay. Positively skewed, okay. Lagi? Anything else? Can you comment on the different hardwood concentration? Can you comment on the tensile strength of different hardwood concentration? 10% wider the quarter range. Yang mana ni? Can you comment on the different, the tensile strength of different hardwood concentration? Between 20% has the strongest tensile strength. Which 20%? 20% hardwood. I see 20% hardwood. Ini kan apa? 5 has the stronger tensile strength. Okay. So, Antonius, you said that 5% is for positive. 5% hardwood lah. Ni bukan 5%. 5% hardwood concentration have positively skewed. 10% hardwood. Hardwood has, so let me betulkan kat sini. Alamak, tak boleh copy. Copy that. Paste. So for 5% hardwood concentration, this one is 5% hardwood concentration. Wood concentration. Okay. That's the strongest tensile strength. Correct? So what can you say about all these apa tu, 5% positively skewed, 10% widest interquartile range, blah blah blah. So this means that different hardwood concentration, different hardwood concentration shows different tensile strength. Okay, differ in tensile strength, and they seem to have an increasing trend. Increasing pattern lah. Less hardwood concentration, hardwood concentration. That means you got the more, the higher hardwood concentration implies you have higher tensile strength. Betul tak? Kan? You got 5% ni. So basically, different hardwood concentration ada different tensile strength. And then the more you go up to the percentage of the concentration, then you've got a higher tensile strength. Okay, that means when you treat your object with different treatment, then you would have some variability here. Yeah. What about within each treatment? So within each treatment, you can see Antonius, you mentioned that within, what about? So what about, uh, so here you've got different variability for different treatments, for different levels of treatments. Okay, so, yep, let me write it here like quick. So yes, you got different variability for different levels of treatment. Okay, this is for between treatment. So for between treatment, between different variability for different between levels of treatment. Okay, that means dia berbeza lah kan? Berbeza. Okay. What about within levels of treatment? So this is one. What about within levels of treatment? Can you comment on that? Within levels of treatment, you can see that macam Antonio cakap tadi, kalau you tengok 5% hardwood concentration, you can see it's positively skewed. What about the rest? The rest, so this one is positively skewed. That means, what does it mean when it's positively skewed? That means the observations here are not similar, right? So you also have got variability within that. You can also observe. So you can also observe different variability. Betul tak? So between treatments, you nampak ada perbezaan. Variability is perbezaan. Dalam hardwood to itself, if you apply it the same hardwood concentration, you will still get variability. Okay, so we can also observe that even when you apply the same hardwood concentration, percentage of hardwood concentration, you can also see variability. Also show variability. Okay. Do you think this is what, good? Is it should this be the, do you think this is good? Faham ke? Kalau you apply, itu saya cakap Melayu sorry, moment, I'm going to speak Malay for a while. So kalau you apply concentration yang berlain, means you punya tensile strength naturally akan jadi lain. Okay. So dia ada variability. So faham ke? Response please. Can you hear me? Do you understand the question? Couldn't hear clearly. All right. Okay, kejap. A bit delay. Alamak, kenapa Alamak, kejap. Cop. Saya check saya punya internet. I'm going to use my phone. Hang on. Bentar. Now can hear. Sekejap, saya guna phone lah. Phone saya, I title from my phone. Pula. Masih boleh dengar ke? Okay, right. Okay, macam gini. Right. Tadi I was asking, when you apply different hardwood concentration, you can see that you've got different variability. This is logical, correct? Because when you apply different treatments to your experiment, then you would expect to get different results. Okay? But when you apply the same thing to your experiment, you don't expect this to be different, right? You don't expect variability in your observations. Betul? You don't expect different variability when you apply the same treatment to your observations. Betul ke? Kan? Okay. So, if this is the case, that means if you apply the same thing to your experiment, you expect less variability. Tapi macam ini, contohnya for 5% hardwood concentration, you can see there's like positively skewed here. That means observation tu is more concentrated here, but there are observation that lies up here and down here. Okay, you can see less variability in 15%. Kalau 15%, you see that the length of this box plot is shorter. Tapi still, there's some variability, but it's not much. Okay, so my conclusion is, when you apply the same level of treatment to your experiment, you should expect less variability. But if you see more variability, that means that there could be an error there. Okay. So here you observe. You observe different variability. So this is unexpected. Okay. Or so we can check if there's an error. Okay. So if you do your experiment, you apply benda-benda yang sama, you expect dia punya observation lebih kurang sama. Okay. Tapi in this case, you can see that dia lain banyak ni. So that means you need maybe dalam experiment you need to check kenapa when you apply 5% dia berbeza. Okay. So later on kita akan tengok macam mana how to see the difference between hardwood concentration based on these two things. Between within treatment, the variability within and the variability between treatments. But bila kita nak cakap, when we want to say, oh, there is different hardwood concentration would give different effect on the tensile strength. We can't just say between treatments. We need to comment on the within treatments as well. Okay. Let's go back to our example of speed of cars. So in this case, let's say this is your observations, and you assume your observation come from a big normal population, and also assume that your population variance is unknown. Okay. Let's say you want to compare the difference in the mean of the speed between the two types of tires. Is there any test that you can think of? What kind of test can you do when you want to compare the difference in means of speed between these two types of tires? Variability is the difference between, variability is the difference between the outliers with the quartiles. The difference in the box plot. In this particular box plot, you can say that the variability exists because there's a difference. Dia bukan between the outliers. The outliers is your observation. Quartile is also your observation. So, okay, just sebelum I go here, I'm going to do that. Mana? Just for that, just comment on this box plot here, referring to Cham's question. So normally for a box plot, the outlier is here. That's why you see these are outliers. Most of your data would concentrate here. So for a box plot, this would be your median. This is this would be your quartile into quartile range. Okay, so tapi the bottom line is most of your observation is concentrated here, but there are some outliers there. Okay, so kalau so let me just draw ni. Kalau you ada box plot, katakan, so ideally, kalau this is your tensile strength and this is 5%, oh shit, let me just, this is 10%, 20%. Okay, contoh macam ini. Of course, you expect you punya box plot contohnya macam ini mungkin pendek je dia punya apa namanya? Dia punya box plot. But you see that you would have an increase in trend for each box plot. Tapi dia punya size tu, dia punya length of your box plot is too small. So there isn't any there's not much variability here. So ideally you would like to have a plot like this. Okay, different percentage, different tensile strength, but within the percentage you would want a very small length of box plot. Okay, no slides? Tak ada slides ke? Oh my god. Click. Can't see. Alamak, resume. Stop, resume presenting. Oh. Okay. Nampak ke? Can see. Okay. So tadi Cham, you ask. So ideally, that means here you've got less variability. Variability tu patut ada because when you do experiment, you would observe different. I mean, dia punya value would be different, but not so much variability as you can see from this slide. Nampak sini? Ni kan, this slide kan, you can see very much variability here. So ideally, you would like to see this. So here you've got between variability ada variability you have, so which is good, and within variability not much variability. So ideally you would want something like this. Okay, all right. So let's say you have two types of tires here, 60 and 24 inch, and you assume that your observation comes from a normal population. So, and then you want to compare the difference in means of speed between two types of tires. Remember, this is your speed. All this is your speed. This is your observed speed. Okay. You want to compare the difference in means of speed between two types of tire. Can you suggest to me any test that you can use to compare the difference in the means of speed? Class? Can you suggest a test that you can use to compare the different means of the speed between these two tires? Boleh dengar ke? Test, hypothesis test. What kind of hypothesis test? What parameter that you can use? T-test of the means. So T-test, yeah, so it's going to be T-test of the means kan? So in this case, kalau you nak buat macam ini, that means you can imagine that you have two population, betul tak? Nampak tak two population? So ni dah jadi, it looks like the one that we have done before, right? So here you have apa nama dia? Two populations. So this is like a two population case. This is your sample. Okay. So for you to compare the difference in means, therefore you can use a t-test with levels in a factor. I.e. here you might have, so here you have mu1 equals to mu2. Dia nak compare the difference. So mu1 not equals to mu2. Correct? The statistics is going to be t-test with x bar 1 minus x bar 2 minus mu1 minus mu2. Okay. Over. Dalam ni, dia assume same population variance ke? Let me see. Population variance unknown je. Okay, so here you would have, so since population variance unknown and small, okay, so etc. So this one is S1 squared over N1 plus S2 squared over N2, because it doesn't say population variance equal. Okay, so this would be the test that you do. So this is your first step, second step, like you do when you do hypothesis, and the third step. Okay. All right. So now, but however, what if there are more than two levels of treatment? What if there are two levels in one treatment? So here you've got the treatment is tire and you've got two levels. So I can view this as a two population problem with sample size as follows. Okay. Tapi what if you have more than two? For example, like this. Oh, sayang. Ni. So here we also want to look at the speed of cars, and we're going to use one factor. So this is one factor, which is just the size of tire. But now, how many levels of treatments are there here now? How many levels of treatment? So you got 4, right? 1, 2, 3, 4. So you test on different types of tires. You got 16-inch tire, 18-inch tire, 19-inch tire, and 24-inch tires. So you've got more than 2 levels here. Okay. So if let's apa tu? Imagine you've got observations like this. So you've got and you assume that observations come from normal population variance unknown, and let's say you still want to compare the difference in means. Okay, in means. Therefore, you still want to, if you're doing a test, you're going to test on the mu. Okay, but now you've got 4. Okay, so how to do this? So if you do your t-test, you can do a t-test on this, but if you do a t-test, listen carefully. If you can do a t-test, but if you do a t-test, note that a t-test, mana t-test? Mana tadi t-test? So if you do a t-test, you can only compare between two benda, x bar and x bar 2. That's how the formula of t-test works. You only have two parameter, mu1, mu2. So you can only compare two population at one time. Okay. If you do a t-test here, you need to do, if you do t-test, can only compare two population at a time. Population at a time. That means you need to compare this one, that one, that one. So you have to, so there are too many variations. Too many variations means that you need to do many t-tests. Need to do many t-tests. Okay. So what does it mean when you do many t-tests? This one is not in your textbook, but if you do many t-tests, remember one test would give you one alpha. For example, I can do 0.01 type 1 error. My type 1 error is alpha 0.1. If I do the second t-test, the second test, I would have another 0.01 type 1 error, because every test that you do, you have an attached error there. Because you're not sure for certain, there's always an error of 1%, 5%. Let's say you one test 0.01, second test 0.1. Let's say you do like 10 tests. The 10 tests you got, so you have 0.01 times 10 tests. So that is a lot of error. So this is eventually you get 0.1% of error. 1%. 10 lah kan? 0.1, so betul tak? 1%, 10% lah kan? 10% error. So your whole conclusion might be suspect lah, sebab too much error there. So this is what you call family wise. Apa nama dia, lupa dah. Tapi itulah, so basically the effect of doing too many tests is you have a many type 1 error. So you punya error akan balloon up. Okay. So one way of going about this problem is using a method that would simultaneously do the test, is using an analysis of variance, otherwise known as Anova. Faham ke? Alright. So what Anova does is it compare the means. Okay. It compare the means of several groups of observation, but based on variability. Okay, based on variability. So you need to understand, when you do Anova, the parameter that you're going to test is the mean. But the way that you compare the means is using the variability. Okay. So these are the assumptions when you do your Anova. These are assumptions that you need to follow. Observations are independent and normally distributed. Samples are independent of each other. And different samples are assumed to come from population with the same variance. So you can see this on your textbook. I think the very assumptions. So these are your assumptions. See textbook as well. See your textbook. Or you can just search for assumptions of Anova. So, okay. So kalau Anova, so you have here, you've got more than 2 population. Okay. It doesn't have to be 4. Okay, but it has more than 2. Okay. So to summarize, if you've got 2 of the 2 population and you want to compare the difference in the mean, then you would do something like this: mu1 equals to mu2, mu1 not equals to mu2, blah 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 blah. But if you do, so this is a t-test, but if you have more than 2, then, and you want to compare the different in means, so it's the same objective, difference in mean, difference in means, but then here 2 types of tires, you got 4 types of tires. In this case, it's 4 types of tires. So therefore, you need to use an analysis of variance. So the way that we do analysis of variance is you're going to compare the means based on the variability. What variability? The variability between the groups. Just like we saw from the box plot. So we look at between the groups. What is the effect of between groups and also within groups? But this within groups, if there exists, it's an error. Sama sayang. Okay. Kalau dia ada effect of between groups, that means it is there. That means the treatment has some effect. But if it's within group, then it means that there's an error there. Mak sayang. Keep. Do you understand me so far? Paham ke? Okay. So when somebody asks, why are you using an ANOVA? Because you want to compare the means, but you're going to use the variance or the variability. The name is analysis of variance. It's a bit confusing because you're actually testing on the means, but you're analyzing the variability. Okay, it makes sense, right? Because tahu apa beza, then you do check the variability. Now, so what exactly ANOVA does is it will decompose. Dia akan partition each observation of your data based on this model. So this is an Anova model. This is an Anova model. Anova model. Okay. Anova model where each response, each data that you have can be written as an overall mean. That means each observation has an overall is the same mean. Okay. Plus some, so each observation has different treatments and it also have different error. So the concept of ANOVA, observation that you have can be decomposed into these three parts: overall mean, treatment, and error. Okay, this is also known as the ANOVA model, which you can see in your page 6 point, section 6.2, page 128. Page 128. All right. So how do we measure this variability? We can measure this variability based on what we call a sum of squares. So notice, consider this is your formula for the usual variance, right? Ni variance yang biasanya kan? This is the usual variance. When you do usual variance, what you're trying to do is you want to see the difference. You take the average difference between each observation and some mean squared over some degrees of freedom n minus 1. So this is formula, consider formula for the variance yang biasanya, yang biasa kita buat. So this is sample variance formula. Now the numerator here is called the sum of squares. So when you do your ANOVA, we're going to calculate the sum of squares of your observations. Okay, using formulas. So what we do is the sum of squares of all total observation. If there's no treatment applied to it, so this would be equal to the sum of squares based on the treatment plus sum of squares based on the error. So the variability of the total variability, so these are all the total variability, variability is equals to the variability due to treatment and the campur variability due to treatment within treatment. Okay, due to treatment. Due to treatment and within treatment. So this should be an error. Okay, so this is the formula that you use. So you can see that it is similar to the one that we have seen before, variance, tapi in this case, based on the each observation, and all these can be simplified to this formula. So this formula is in your statistics table. This formula is in your statistics table. Mana statistics table? This formula is in your table, page 4. Page 4. Okay, in your stats table. Okay, so what we're going to do, we're going to calculate this bit, and this bit. Okay. Okay, mana ni? So how do we carry out ANOVA? Oh boy. Okay. So when you carry out ANOVA, you still need to define your H naught, your test statistics. So notice the difference here. Writing out your hypothesis for ANOVA, there's only one way to do it. So here, if you do a t-test, it's mu1 equals to mu2 kan. So H naught here, since you have 4, so it's 1, 2, 3, 4. Mu1 equals to mu2, equals to mu3 equals to mu4. Now the opposite, when you have more than 2 population, is not like what you do for your t-test. For t-test, it's just mu1 not equals to mu2. But for ANOVA, when you have more than 4 populations here, you're assuming if at least one of them is not the same, then it falls in the opposite direction of your H naught. So for ANOVA, you always write your H naught like so, at least one of mu I not the same as mu j, where I not equals to j, then it is the opposite of H naught. Okay. So note that, oftentimes student will do like this. For ANOVA, mu1 not equals to mu2 not equals to mu3 not equals to mu4 is, mana color lain ah? This is wrong. This is wrong. Okay? It's always at least one of them is not similar, is not the same, then it falls in the opposite direction of your H1. Right? And your F test is given by this mean squeeze of treatment divided by mean squeeze of error. Right. So what is the mean square of treatment? So mean square of treatment is equal to the sum square of treatment divided by the number of treatment minus 1. So this is the number of level. So this is the number of undo. So this would be the number of levels. Number of levels. Treatment levels. Treatment levels. Treatment levels. Okay. MSE is the total observation minus the number of different levels. And notice that this is the sum of squares. This is positive. This is always positive. So therefore, your F test is always positive. So it's always on the right tail test. So this is always here. Okay? Always onto F test because it's positive. Your F test is always positive. Always positive. If you get always positive. If you get a negative, then you need to check again because we're dealing with sum of squares. So therefore, it is always positive. And then conclusion. So all the steps follows. 1, this is the first step. Second step, F test. The third step, and conclusion. Okay? All right. Okay. So because there are so many steps when you do your F test, you need to calculate sum of treatment, sum of squares of error. So an easy way to do this is to draw an ANOVA table. So ANOVA table helps you to write down the results of your F test. So this is so the source of variation when you do your ANOVA, you know that you have between levels, okay, due to treatment, and within levels, which is an error. So you need to calculate the sum of squares of treatment, and then sum of squares of total, and then sum of treatment, and then you just minus this out to get your error. Okay, so similar to this, here you just need to determine how many levels of treatment, -1, how many total observations, -1, and then the difference is your number degrees of freedom for your error. Mean sum of squares is treatment divided by degrees of freedom, you get this. This one divided by this, you get that. So your F test is just the ratio of these two. Treatment between levels and error. Okay. So this one is like from here. Okay. So it's just a method of calculation. Anova is a method of calculation, and you need to write you need to okay. Okay. Let's do an example. Example, here you have electronics engineer interested in the effect of tube conductivity of 5 different types of coating for cathode ray tubes in a telecommunication system display device. So these are the following conductivity data. So the observations are conductivity data. The question is there any difference in conductivity due to coating type? Maksudnya, is there any difference between the coating types ni? Use alpha 0.01. Okay. So use alpha 0.01 is an indication of a hypothesis test. Okay. So in this case, you've got 1, 2, 3, 4, 5 populations. So you know that you can't do the usual Z or T test. You need to use an ANOVA because of there's more than 2 population. So here you're going to write your hypothesis test. You're going to do the definition. You're going to do the test statistics. You're going to do the decision rule and the conclusion. Okay. So the only part that you need to do more, you need to do more analysis is on the ANOVA table so that it's easier for you to calculate your F test. Okay, so let's calculate the sum of squares first. So in exam, because this is quite a lot of calculation, so you need to get yourself organized. I suggest every time you get a question like this, calculate all these stuff, all the total, and you can easily do it from your calculator. Use calculator. Use mode in calculator, or you can use your Excel. Okay, write this out first. So because you need to calculate for sum of square treatment, sum of square total treatment, and error. Error is easy because it's just the difference between some SST and SS treatment. Okay, so for SST, the formula is like this. So you need to understand what the formula means. So this is Yij squared. Yij squared means each observation is squared up. Okay, like this, 143 squared, sampailah 142 squared. Okay, again, this one use calculator as well. Don't calculate 143 squared plus 152 squared plus, do not do that. Use your calculator to calculate the sum of squares of the total observation. Okay, minus y dot dot is the sum of your observations. The sum of your observations squared. Lemak,